Welcome to this week 4 session 1. Right now I'm alone, but it's okay. I will get started soon. First thing I would like to talk about is about the homework. I know probably many of you feel the homework is a little bit more challenging, but that is okay actually. As you may know, most of the homework are from the textbook. So that is about the standard that the programming language courses will have. So if you have questions, you are welcome to contact me, and actually any question will be welcome. And the topic doesn't have to be limited to the homework or related project or something. You can have any question. I all welcome them. That's the first thing I would like to talk about. Second, I would like to talk about some recent development. Okay, about homework, I have one more thing to talk about. Some of you, about maybe 20–30% of them are behind on homework, and actually I would like to encourage them to submit earlier, and because there are still many coming, so try your best on working with these homeworks. And I believe the homework is the most detailed, will have the most coverage on the topics in our textbook, and try your best. And also, some of you may have observed that I haven't done the grading for homework 1, 2 yet, because I need to, I want to have everybody to turn in before I do the grading for everybody, because I also need to send out the homework solution. So if I send out, then those people who haven't turned in cannot turn in. So I would really suggest them to try their best to turn in, so I can finish up these jobs. And I know there are certain things that make you slow down. So, but the thing I can suggest is like try your best. And it's also very important that you keep track, keep in pace with this course. So otherwise, after the last few weeks, you probably have a lot of workload. And also, this course we have done chapter 1 to chapter 4, and as I said, 2, 3, 4 are the I believe would be the toughest ones. So actually, we are through the process of the compiler and language related design related issues, and now from this chapter 5 and on, I believe it's a little bit more informal, or I should say more not as technical as before, and more like a topic review type of work. We no longer go into those fundamental math and fundamental language design stuff. We probably will go back a little bit, but not as much as before. Now let me get started for this new information about the TensorFlow processing. Okay, let me check if I turn on the recorder. Okay, I just want to make sure because I don't want to waste my time. Okay, about TensorFlow processing unit, TPU. And this is very important because nowadays the artificial intelligence or machine learning has become so popular, and it has been penetrated in many fields, including automotive and robotics and unpiloted airplane, something like that. And we have a lot of applications to be developed, and they all depends on the processing speed. And the processing speed of the machine learning and artificial intelligence actually will require new programming paradigm other than the manual machine we have so far. So some sort of new computing paradigm will be needed. And as I mentioned, programming language is not limited by the programming paradigm that I mentioned in chapter 1. Programming paradigm is the thing that programmer will be thinking about, will be reasoning, will be actually designing something on, will be the programming paradigm, some kind of computing model that's actually you are operating on. But and the programming language is only a tool that allows you to realize your computing model. And different computing model, you will come up with different language and maybe also different hardware. And this TensorFlow processing unit is a new unit, maybe will be a new core processor to be implemented in our computing system to help the CPU. And maybe it's a standalone and will need new CPU as well, but it will help to speed up the speed for the artificial intelligence new computing model. So Google has this dedicated TensorFlow processor, and it looks like this. And here you see a lot of maybe aluminum plates. These are it's a heat sink, so it is look like it's not water cooled. It is actually still using metal, and I think that its heat dissipation probably not too. It's not that bad. So, and as you can see, there are some processor on the side and some memory this side, and the I/O probably over here, and the PCI Express 3 probably is here, something like that. Okay, and it is used to support different programming paradigm. Say this is deep learning, and this chapter 5 we are talking about a target model, target machine architecture, and that is one kind of computing model that we support, the monument machine. And this TPU is another. So actually it supports different computing model. You have the training, you have untrained neural network model, and then you train it with past knowledge, and then you use the trained model to do computing. So you start to apply some data in and do inference. And so here is one inference engine, and then you will get this probably is a vision or pattern recognition for 2D, and something like that will be used to help to process a lot of data, and we call it informatics to help to use the neural network. And this is one of the computing model, and neural network research have been there for maybe more than 30 years. And it is still trying a lot of different hardware, and it will require new software, new processing unit as well, and that's why Google is working on this. And this, I believe, will be very important. Maybe also will support some machine learning project, like maybe AlphaGo or something. I don't know, but this is something that they will try to speed up the processor. And the TPU design is like this. You have PCI generation 3, PCI Express generation 3, supporting 14 gigabit bytes per second I/O, and then they have metric multiply unit. The reason why they need such a big metric multiply unit is because in neural network they are using accumulation model, and each neuron will pass data to the nearby network neuron unit, and they try to pump the data in systolic array type, and so they have systolic data set up to pipe into there, and also this is the data pass and pass through here, and the control is in red. So apparently the instruction is fetched from here and passed to the control unit. And apparently the architecture is quite different from what we are going to talk about today. But I show this case just to let you know that the computer architecture is keep improving, and also the thing that we are going to talk about is not unique, and it's not the only hardware project that's available right now. We have CPU, we have GPU, we have this one TPU, and maybe we also have some fuzzy logic processing unit or something. These will continue to be an important field, and programming language is something that will help to put the proper computing model on these different hardwares. So we talk about a compiler in chapter 2, 3, 4. Those are the old language or existing language design tools, and maybe in the future we have new tool coming out, or maybe we use these tool, continue to use this tool to develop some language on this new processing unit, or maybe we have combined things, or that could happen. So that's why we continue to talk about these compilers' importance. And now we move to the back end a little bit. I will cover this today. And this is the PC board. And as you can see, look, as you can see right here, probably this is the memory. This probably is the memory bank. And this one is the processor. And on top of this, probably that is the big aluminum heat dissipator and something like that. And they have the PCI Express Generation 3. And there is inserted, it can be inserted in the slot for SATA disk, probably through the PCI Express interface right here. Benchmark comparison. So for every hardware, we actually need to run some benchmark to test its speed. What is benchmark? Benchmark is some standard program that you load to some new CPU so that you can compare the speed of the program to test how good your hardware is. And this benchmark usually will be compiled by some new compiler for the new hardware. So let's look at this benchmark result. So benchmark servers use Haswell CPU, K80 GPU. K80 is NVIDIA's GPU, graphic processing unit, and this Google TPU. And let's look at this. The clock rate, this Haswell is higher, and these two are comparable. The die size, square, this one is the die size. This will be probably divided by 100. It will be about 6 centimeters square, 6.7, about 6.6 centimeters square. So 6 is about 2.5 centimeter by 2.5 centimeter, something like that. TPU has not been released yet, but power dissipation is way lower, probably only half of them compared to them. And tera operation per second, this is another important thing that people look at. The number for this TPU is way bigger, so it can process more operations with less power dissipation. That's its advantage. And as I mentioned, it is not using the water cool scheme, but it is using the metal heatsink. So look like the power is not too big compared to these different processors. And they have on-chip memory size. These are important. Okay. And which benchmark server, so look like the power still be lower, but not that lower actually. And okay, so here are the performance comparison. You use the CPU, GPU divided by CPU is the blue, And then this TPU compared to CPU, TPU compared to GPU, TPU compared to CPU, and TPU compared with another GPU. Actually, this number, as long as it's greater than 1, it's quite good actually. So actually, this benchmark is way better. Okay, that's the first thing I would like to talk about. Second thing that I would like to talk about is, let me check. We continue our talk on the Bison and Flex, and this is also related to our chapter 5. I will give you a quick overview on Bison products using the Calculator 3 project as an example. Okay, before I go on to it, let me check if somebody is around. I'm alone today. Anyway, let's get started. I have covered the Calculator 1 and Calculator 2, and they are from the lexical analyzer and then a very simple parser. And this Calculator 3 has 3 different output formats. I call it the product for the Bison tool. We'll talk about this today, and it is a better example for the Bison program. This version of calculator is substantially more complex than previous versions. Major changes include control construct such as if, else, and while. In addition, a syntax tree is constructed during parsing. After parsing, we work the syntax tree to produce output. So this one actually means like we construct the syntax tree during the parsing. After that, we evaluate the attribute grammar, something like that. So you will be doing that to generate the call, taking the action routines that's supporting the syntax tree, so that you will generate some output. And these output, I call it Bison products. 3 versions of the tree walk routine are surprised. So you have 3 different ways of working through the attribute grammar built by the parser. And then there are 3. One is an interpreter that executes statements during the tree walk. So during the evaluation flow of the attribute grammar. And the second one, you can walk through there and create a compiler that generates code for a hypothetical stack-based machine. Third one is you can generate a syntax tree of the original program. So this one actually should be considered a intermediate form. So basically, your program actually can generate a interpreter. So you will create a interactive program that can take users' input and generate output for him, or you can have a compiler, and that will translate a source code from one language to the target machine code of another language, and maybe both of them are source code, maybe both of them are one of them are assembly code or object code or machine code. And the third one is to create a syntax tree. The syntax tree usually have different format. As I mentioned, it can be AST, it can be a GIMPLE file, it can be a CFG control flow graph, or it can be the SSA, depending on how detailed you want to have. And we know that SSA should be considered as the intermediate form, but as we mentioned in the semantic analysis, the intermediate form generation and also the semantic analysis, sometimes they are mixed together. So it's very hard to divide what it is. But what we mentioned here is actually the result of the Bison program, say a parser file, parser.y, anything like that, will be a program that you can take interactively, or something that you can translate some code, or the third form is it can end up with some intermediate form, so you can process later. These are the three forms that is generated. So one Bison file, you put in your Bison, your parser.y, and then you will generate three type of program. And one is the interpreter, takes source program in and can provide the output to the console or your output file. Or you actually take the source code and Bison generate a compiler, and you can actually generate some object code. Or the third one, this one is a control flow diagram, control flow graph, and it can generate a graph or tree or AST. So a simple program like this, for the interactive version, it can generate a result that you ask for, or you can actually compile to some assembly code or machine code that actually I'll show you this later. And the third one is can generate a tree. We will also see this today. And in the process, we generate a simple table and the token. The include file contains, this include file actually is the .h file, y.tab.h file contains declaration for syntax tree and the symbol table. Symbol table SYM allow a single character variable name, a node. It can be a variable, it can be some node, and node usually are the terminals or the non-terminals. So a node in the syntax tree may hold a constant, that's constant node type, a identifier ID node type, or an internal node with an operator that's called OPR node type. So that's constant, ID, that's ID, upper, that's operator. A union encapsulate all three variants and the node type. A union is a data type in C language that share one memory location with with many different data type. And right here we share a constant data type, an identifier data type, and a node for operator data type. So three variant and the node type is used to determine which structure we use. So there's a variable used to determine which one we use. And the next input file, is the calculator 3.l file. Any .l file contains patterns for variable and integer token. In addition, tokens are identified for two-character operators such as EQ and NE. EQ is equal, NE is non-equal. And so the input file contains the pattern for variable and integer. So two types of tokens. One is the constant or integers. The other one is variable. And single character operators simply return themselves. So there are two types of operators. One is the two-character one, that's equal, non-equal, greater than, those kind of the operator. The other one is single character operator like plus sign, minus, division, and multiplication. These are single characters. So single character you got will be returned right away. Non-single character operator will be considered as a node or token in return, like will build up a node. And integer will be maybe this node type, and variable may be building this ID node type. So that's done by the parser. Those nodes are bound by parser. For next input file, these will be used to generate the tokens, three tokens. One is variable token, integer token, and the operator tokens. And literal, variable, and non-terminals. These are the constant, ID, and the node. But in the YAC input file, we have YYS type. The type, this will define the type of the YYL var value. So YYL value have these three types. One is the integer value, that is the integer, that's the output for the the content of for the YYL variable can be a integer value, can be an index to the symbol table, or can be a pointer to a node. And return value by YYLex, this causes the following to be generated in y.type.h. So type define union, actually the integer value int I value. This one is the type definition. The previous one is the record. So in the parser, actually this is a record, and in the YYLex, that is returned by YYLex, actually is this one is in the lex file, included in the lex file, actually is the output format for the YYL val, and is determined, the type is determined by the parser, and it is defined in such a type. So this is actually a union structural union type definition. That's YYS type, and has three different data type that will share one memory location that will be returned in this YYL val variable. Number literals. For number literals, that is a constant. We actually just convert from string as YY text ASCII to integer. So you actually return to YYL val.I value. This dot is the data field reference for the union. So YY val.I value actually is to access this union data structure in the I integer format. And about this union, we will talk about this at chapter A, the composite data type. So if you are not familiar with C language, just think about there is a certain integer that you can return, but that integer can be interpreted in three different formats. It can be a integer value, it can be a index value, or it can be a node. So basically, the number literal is just read in the text and convert it to a constant, and that will be returned to the parser. And non-terminal node and the terminal node, we actually declare the I value type for integer. For integer token, we will return this. For an expression, we will consider that as an N pointer. N pointer is a node pointer that is a pointer to the parsing tree. So this bind the expression to N pointer and the integer to I value in the YYS type union. This is required so that it can generate the correct call. For example, we have one expression, but that expression has a definition for the integer. So the integer will get the first right-hand side value, and then consider it as a constant, make it a constant, and return that constant value to the left-hand side, become the expression's value. So this is the action routine for this duo, and that will return the integer value. The first one on the right-hand side, interpreted that as a constant, and then return to the left-hand side's value, the double dollar sign. Second, I should generate the following code, so know that YYVSP is value stack pointer, 0 edges, the top of the value stack, or the value associated with integer. So basically this one, if you pop up the value stack pointer and value ival, that actually will convert it to constant, and actually that will be assigned to the YYL val's N node. So that will be the pop out value from the VSP will become the pointer value for the integer node. And unary operator minus is given higher priority than binary operator as follows. So the binary operator, we have the greater, equal, less equal or non-equal, or greater, this greater sign and less than sign. And we have plus, minus, multiplication, division. All of these are binary. Binary means you need to have A plus B, two parameters or two value. And this unary minus is only one operand. And so you have -5. That minus is unary minus. And it is non-associative. And these are left associative. And unary minus, we have non-associative, indicate no associativity is implied. It is frequently used in conjunction with percentage prec, and prec is precedence, specify the precedence of the dual, so that we have one expression defined as minus expression, and this minus, unary minus, has precedence. So you need to be considered first. And the value is the one tuple data that taken from the second of the right hand side, second of the right hand side. This one is first one. Second is the expression value, and then consider that as a node, and that node pointer assigned to the expression. So in this calculator 3, we start to have the idea of node, and the node is the AST. Now we talk about in chapter 4 for semantic analysis. So I will briefly show that to you later for this. Indicates that the precedence of the dual is the same as the precedence of the token unary minus, and the unary minus has higher precedence than other operators. Okay, so that's what it is. Syntax tree. The syntax tree is constructed bottom up, allocating the leaf nodes when the variable and integers are reduced, and when operators are encountered, a node is allocated, and the pointers to previously allocated node are entered as operands. So basically, this is talking about the stack. The stack being entered, push in the operands, and then push in the operator. Operators on top of it, and operator will become the node that actually has those operands under it. And those operands are at the bottom, and those are leaf node. So when you apply the evaluation flow, the value will be from the right hand side to the left hand side, and according to the action routines. And for action routine, don't be scared. It is easy. You just getting the value from the bottom and send it up to its top node, and top node will sum up by certain function. We call it semantic function. Somehow it's accumulation. Sometimes it's taking the largest one. Sometimes it's just taking sum or minus or multiplication. On the tree is built a function called EX. EX is the actually is so-called action. The attribute flow, the program or algorithm to run the first work of the syntax tree. So this first work is actually the evaluation of attribute grammar. So this EX is used to evaluate the syntax tree's grammar. This results in operators excuse me, being applied in the order that they were encountered during parsing. 3 versions of EX. So basically, this EX design, the so-called attribute flow, the design of that attribute flow, the evaluation of that actually will determine whether it's a compiler or interpreter or the syntax tree. So we'll look at that one, the example in calculator 3 later. And let's look at the calculator 3 language. So let's look at the example. Same thing, you can take the C tab that I include in the previous week. Okay, let's look at that. Let's look at our, okay, right here. Let's look at our week 3. And then we have the instruction material. So last week, we actually have right here the collection of flags and Bison example. The CTF file right here include this Bison, include this calculator 3 program. So in week 4, week 4 right here, we have this presentation file. This is called this Bison one, but actually in week 4 we will have this calculator 3 language description, and we will be working on this calculator 3. Now let's look at this calculator 3. So first let's look at this lexical analyzer part. Lexical analyzer part is easier, so I would like to look at this first. You have the this one is the variable. The variable is only single character, so actually you have the YY text that is a string minus A, that would be 0 to 25. That would be the index for the symbol table, so it's S index. And when you return the token type variable token type, you will also get the symbol table index to the YYL value. And for 0 and these are numbers, so you will return the constant integer type token, and with the YYL val with the value of the integer. And right here you have these operands or braces or semicolon that is actually will directly be returned. The string, any pattern in here will be returned. And any of these different keywords or different these are 2-character operators will be returned as different tokens, GE token or LE token or EQ token, and while token or if token. So these are keywords or operands, and white space will be ignored, something like that. This is our calculator 3.L. Calculator 3.Y, actually right here, we have 3 node type. So 3 node type, we have operand node type. So operand node type, you have these, the first one is the operator type number, and then the number of operands. So you may have 2 operand or 3 or 1 operand. And the ID type will be a integer, and this is will take an integer for the ID, and this constant type will take the constant value, and free node will be clean up the free node. So these are 3 different functions that will return the pointer to a certain node, and that will take in a few different parameters in to create a node. And EX is a program to evaluate a certain node. So that's okay. And the symbol table is right here. And union, inside the union we have, these are 3 different variable types sharing the same memory location. It can be an integer or a index to the symbol table, or it can be a node pointer. And right here we have the integer variable. These are different tokens, And right here, we also have the while if print. These are keyword tokens. And these two are the non-associative keywords. And right here, the operands, left associative operands and non-associated unary minus tokens. And here are the node pointer definition. These three non-terminals are considered to be a node, would have the node pointer. So top level program will be a function, and that when you finish the function, we will generate a exit 0, and that actually will be finished. So actually, what you need is your program. You can just click semicolon, that will finish the program. Okay, and then right here you have function. You take in the function and then statement. A function can be function continue to, this one is recursive. So you will evaluate a statement, and then after this statement will be the top level execution. So you can have the statement after statement after statement after statement. This is how this recursive will do. And every time you execute one statement and get a value evaluated, and then we'll free that node. And right here you have the statement definition. You have different statements, and I won't repeat this, but anyway, this will calculate the node, construct a node, and return to the statement nodes under the, will be construct as a node to the statement node. And same thing for this different expression or statement list. Okay, and here are the function to construct a node for a integer, to allocate memory for it, and then assign value into that and return the pointer. Same thing for ID node and operator node. So these are the functions that we define in section 3 in order to process the nodes. So in this kind of the YEC file that has an AST, you need to construct a parsing tree. When you construct a parsing tree, you will need to define these different tree nodes in the section 3, in the part 3. And as we see the calculator 1 and 2, we don't have this because at that time we only evaluate one single statement or one single line value. Actually, the program is not structured. The program is not structured, so actually you are operating in interpreter mode. So each line of the operation you process right away. There is no program node to be constructed, no AST required, even though there might be some simple AST, but there is no node being constructed, no parsing tree being generated. But right here show you a very basic type of how to construct a tree, and we using this Bison tool. And then after that, you have the main program defined right here, and actually run the YY pass. And that's the main program if this is the main. But usually you can have different C program that may have its main or something. So that's this calculator 3 that way. Now let's look at another program. Let's look at interpreter based. That's calculator 3A. That's interpreter based program. So we have this calculator 3A as open with a Notepad+ as well. And I'll show you. Actually, right here, it only defines one function, is the EX. And this EX function actually is the attribute flow program, the algorithm that operate on the attribute grammar tree, the AST. So as you can see right here, it is actually a switch case statement type. So it's nested switch statement type. So it is actually an ad hoc evaluator for the attribute grammar. And once you take certain node in, right, and then these are the left-hand side. The left-hand side, if the node is a constant, then you return the node's constant value. If it is a variable type ID, return the symbol table's index value taken by the node's ID value. So the ID, the variable node, will have one integer and use that value stored in the node. This should be the attribute. So this is the node attribute of the integer that is actually showing you the symbol table. So remember that. Let's put it up. Okay, let me bring it up. Chapter 4, semantic. Let's move down to the last page. Okay, last page. Right here, this one. Let me try to make it bigger. Right here, you have a symbol table. On each node, you have this S value, right? This S value is the symbol table's index. So this one is this ID.I value, this pointer pointing to that one. That ID value being returned. And look at the symbol table. So that S is this P pointing to ID.I value. Its value will search into the symbol table and get the ID value, return that result from the symbol table. And if you see a operand, you will just evaluate down to the operands, because operand is on top of a certain top tree, and then they are operators are on top of the subtree, and then they are operands under it. And then you go through that, you evaluate that. So interpreter type, you directly evaluate the tree and then send the result back. That's the interpreter. I'm sorry, not this one. Let's look at this one. For compiler type, it is actually different. It doesn't evaluate it. Instead, it will generate the code for you. For example, you generate the assembly code for you. Add, sub, mar, and then you have compare little than, compare greater than. These are assembly code. So here are several assembly code being inserted here, but it is also a ad hoc algorithm. Let's look at the graph part. Graph part is the G part. Let's open it. The graph part right here, actually, you will build a tree by creating new node for the evaluation tree. So it's trying to build up a tree using a new node type, and then it's a linked list with the tree node. So you will add node and then define some node and then throw those nodes out in a graph format. So that's that. Now let's try to run it. Okay, let me just bring up one more thing. Let me bring up this BO1. Let's open this BO1. So in BO1, we actually will convert the Bison file to this one is convert to Bison file, and then you convert the table, put into the lexical analyzer, and then generate a dev.yy.c, and then dev.yy.c with the output for the Bison file. You compile it to generate these two object file, and then you with the evaluation function, 3 different evaluation function, the attribute flow, they use different algorithm, you can actually generate the 3 executable files. So let's look at the this again. For this graph, actually that tell you that the parser itself is the same, but the difference that make these 3 versions is on the EX function, the evaluator, the ad hoc program that used to generate different versions. That one actually made a difference. So the EX file actually made a difference. So that's our BO1 batch file. Now let's go back, and I would use the Shift right mouse click, open command window here. Right here, let's type dir to look at this directory. And now let's run BO1. That will build the whole program. After that, let's try interpreter base. That will be calculator 3A version. In this program that I can do A equals 3, B equals 4, then print A plus B, then C equals 7, then print A times C plus B, something like that. This is the interpreter base. And then I hit semicolon and hit Control E to get out of it. So this is our interpreter. Now let's try this calculator 3. B version, that's compiler. Before we try this one, let me open the simple program. This simple program is in calculator 3 language. Let's open with Notepad as well. So this is the one we show in the slides. X set to 0, and then while x less than 15, and that's printed out. So now let's run it. And let me feed the input file from this sample. My keyboard doesn't cooperate. Sample. Sorry, calculator 3. So run it. Wait, my keyboard doesn't cooperate. It doesn't function well recently. Okay, it's done. So I get this assembly call for this calculator 3B, the assembly format. Oh, I'm sorry, the compiler format version. Then I use calculator 3G from the same sample file, calculator 3 language, and you will generate a tree. Okay, that's the function for this calculator 3. For the detailed grammar and how to write this code, I will keep introducing in later lectures. Now let me check anybody on board now or not. At this moment, still no. Okay. Everybody are quite busy. Now let's look at our chapter 5. Chapter 5, Target Machine Architecture. Overview. This chapter, I would believe the most important part is the instruction set architecture. So instruction set architecture is the interface between your software and the hardware. So software you can fight, but the hardware you cannot move. You have to stay there to support them. So if we have the target machine structure like this, how can we develop from scratch or from ground up? So for example, we would like to develop a new computer, and let's call this instruction set architecture X. We need to design this instruction set architecture X first. So we got the whole instruction set architecture done before we doing this design. And after that, we actually need to use the existing machine, say Intel x86 format, and then build a simulator for this instruction set. And we write some assembly code for this assembly set, this instruction set, and then simulate it on existing machine. So you will know whether this assembly work or not. After that, we write a bootstrapping BIOS using this, and then we actually construct a compiler based on the assembly code we have. This compiler operates on the simulator, and then we build the hardware. Once the hardware done, we had a processor, memory, I/O, those things done. Then with this bootstrap I/O unit, we actually will be able to build a emulator instead of the simulator. So this set of assembly and the compiler can still work with the emulator. And with that, we build our first simple operation system and I/O unit. And on top of this operation system and bootstrap BIOS, we build our assembly on the emulator or on the real machine. And then we try to build a compiler on top of it. After that, we build a virtual machine JDK or the interpreter based on the C compiler. We call it native codes, or Java or Python virtual machine. And then we build an application program on top of it. So this is the order that we build up our new machine. And then we take away those simulator environment. And right here, I show this is borrowed from chapter 15.2. Our discussion on the compiler end at chapter 4. In chapter 5, we introduced this instruction set architecture, but the back end of this compiler will be discussed in chapter 15, but somehow our 8-week schedule doesn't support this. I won't go into here, but this chapter 5 will be strongly related to chapter 15 because we need to talk about the instruction set architecture first. We have a target machine description before we can talk about how to generate the code and optimize it. And this is the so-called GCD program with the syntax tree and the table. And as I mentioned, here are the symbol, type, index, and symbol and types. And you have the AST like this. And that AST being converted to the control flow graph. This is a CFG we mentioned about actually in chapter 15. Well, you will talk about this. This is actually close to intermediate code already. And after the CFG, you will do SSA, static single assignment, and put in the file function or something, and then do optimization. So this is what we will discuss in chapter 15. So chapter 5 and chapter 15, backend compiler issue are in chapter 15. So from GIMPLE, SSA, optimization, Un-SSA, RTL, SM, and the machine code. Chapter 5 focus on ISA, that's the interface between the machine and the software, memory coherence model, and chapter 6 we talk about loop level optimization. I'm sorry, in this chapter we also talk about loop level optimization, and some part of chapter 6 also discuss this. Now let's look at the lecture 1, the computer architecture and programming language. And basically, computer architecture issue like impact programming language basically is about how you generate a code based on the instruction set. So before we do the code generation or optimization, let's look at the different issues that will impact your programming language. One is the instruction level parallelism. The other one is SIG versus RISC. And another one is superscalar. So this actually trying to explore the parallelism between the instructions and data. And these are the 4 techniques that have been invented to optimize them. So, and writing the backend need to be based on the techniques developed here. And there are certain platform dependency issue for the backend as well. You have virtual machine interpreter and native code compilation, or just-in-time compilation. These all will impact the backend design for the compiler and the language. And also in chapter 13, you need to support the multi-threading. And for multi-processor environment, you need to support the multi-core, multi-processing. These are the issues for the backend support for the programming languages. Programming language and the compiler design. So you try to take the most advantage on the parallelism and perform optimization, including vector processing, loop unrolling. The unrolling is trying to do parallel on the loops as well. And also the task level parallelism, like concurrence programming. Now let's look at this. This is the pipeline. Traditional architecture is like this. You have some data paths. You fetch the instruction from the RAM, the main memory. But right now we have cache. So actually this one is a little bit simplified. And that instruction got decoded to determine what instruction it is. And you fetch the data either from register or memory, and then provide those data and instruction to ALU, arithmetic logic unit, and you do computation, get a result, and then you store back to register, or you actually write back to memory, and then you fetch, and then you send the result right back to memory, or you write back to register. But this is not pipeline to design. So we try to break down this architecture into pipeline design. We break down to 5 different stages: instruction fetch, instruction decode, and register fetch, and then execution the program. So this usually is EX, this is IF, this is DE or DF, and this one is memory access MA. Sometimes these are in different order actually, and right back depending on the architectural design. And memory hierarchy. The reason why RISC machine become popular is because of the caching of the data, and then we simplify on the instruction set. But main issue that made that occur is the memory hierarchy, because our register is so fast, it's in nanoseconds, and level 1 cache is also in nanoseconds. Level 2, level 3, that's on-chip, but further away cache, it takes tens of nanoseconds. And off-chip cache actually is about 50, that's tens nanoseconds. And memory can go to 100 nanoseconds. That's off-chip to the memory SRAM. And then flash is in the microseconds and disk in milliseconds and tape in seconds. So these are the memory hierarchy. So a lot of instructions have been used to optimize the access time for these different memory hierarchies. Okay. So the pipelining, the reason is because if you need to access, say if you need to access the main memory, it will take a long time. So this actually currently each clock cycle time is maybe 3 gigahertz. So it's probably 600 times slower than the CPU clock cycle. So your clock cycle cannot wait for that. So you have to do some caching, prefetch the data into the level 1 cache or level 2 cache, make it faster. But even that, you still burn maybe 2 clock cycles away. So we try to prefetch the data into the register as fast as possible and try to make sure that you chop down into 5 stages so you can perform pipeline design. So pipeline means you actually, every clock cycle, we initiate one new instruction if possible. If there is a certain memory access that you need to wait, then you have to wait. But we call it pipeline store. If your pipeline is not stored, they will keep operating like one clock cycle, one instruction format. That is the spirit for the RISC machine. And it actually depends on the instruction level parallelism, whether the data can be shared. Is there some data dependency? Actually, that is the topic people would like to explore. And here is the single cycle and multi-clock cycle and pipeline comparison. Single clock cycle means one clock cycle, I will do one instruction or one stage. And multiple clock cycle means I will load for more than one cycle or longer. Superscalar is a improved version of the pipelining. We actually not fetching one instruction at a time. If there is no data dependency between 2 instructions, then we can actually fetch 2 instructions at a time and then perform both. So theoretically, 2 instructions superscalar with pipelining, you should perform like 10 times, almost 10 times faster. And if you only have pipelining with a scalar instruction, you should get a degree of close to 5, but it will be less than 5. So superscalar, you can instruction set, fetch instruction, maybe 2 at a time, put into queue and dispatch it. And at the same time, you can use multiple processing units, so you can have more than one instruction got served by the CPU at a time. So here is the super pipeline design. And super pipeline is different from superscalar. Superscalar, you fetch 2 instructions at a time. Super pipeline means that, okay, I think that I can further chop the one clock cycle to half. So I actually pipeline with a half cycle clock time, so make it actually more dense or more compact. That's called super pipeline. So we have the base machine pipeline, and then super pipeline or superscalar. And super pipeline theoretically should also get a degree of 2 improvement compared to the base pipeline. But in reality, you won't get that much. And now after that, it's called VLIW, very long instruction word. And that one actually is, I get the instruction, but I actually execute 3 or 4 of them together. And this is called the VLIW architecture. So basically, I got an instruction, I fetch the instruction, but at the same time, I execute 4 different instructions at a time. So this actually gives you a higher performance as well. But you need to have more functional unit line up. Then the last one is out of order execution. Because some clock cycle may be jammed, and this out of order execution can be done for all the different instruction level parallelism that we have talked about so far. because sometimes they are data dependency. Say we have this first instruction, we try to access the memory, but during the memory access, the next one cannot execute because of the data dependency or something like that. So you actually have to wait until the previous one finish, then you can do something. But if we move it to have the out of order, so the second instruction write back can be faster than previous instructions write back. We call it out of order completion. Then we can actually get rid of this, actually make the best use of this waiting time for the clock cycles. So because the execution is out of order, so you need to make sure there is no data dependency so that you can actually explore this instruction level parallelism. So try to make the best use of the idle states. And here is one out of order execution engine, microcore based. So you have the instruction buffer, instruction buffer, and then put into the 32K. I cache is instruction cache. You cache it from the buffer, and also you actually has the branch predictor to help to look at the branch, how well it will branch, and then you get the instruction to the fetch queue, and actually this branch predictor will help you to decide whether it's a yes pass or no pass. We'll talk about this later, but you fetch the instruction, and then you interpret it into microcore, and at the microcore, you actually use the instruction just like a program, and you actually, here is a fast interpreter. We call it microcore, and the microcore being used to perform instruction to be executed, and then you can perform the 40-point operation or integer operation. And at the end, you have to retire all the data and then actually provide sync point to make sure the program is still in right coherence level. And in addition to the out of order execution, we also have some way of doing that. We call it reservation station. That actually is similar idea. But actually you would, at the reservation station, you may rename the microcore operators, and you will rename it or rename the register so you can perform the out of order execution. And at the end, after the execution, you reorder the buffer and make sure that the data is consistent. This is called reservation station. So newer design for A7, A15, you have more complicated instruction structure. The data path, you have a instruction execution flow are more complicated. And multi-core is to put multiple CPU at one die, and you can have multiple threads running on one CPU, and this provides you the task level parallelism. And task level parallelism will be discussed in chapter 13. That's our week 8 topic. And right here, I talk about multiprocessing and multi-threading. And as you can see, we have concurrent task execution. And here are 3 different types of concurrent tasks. You can have multitasking, you have multiprocessing, and you have preemptive and cooperative. Multiprocessing is different from multithreading. Multithreading can be virtual, 1 CPU or 2 CPU, but that is actually have one app but running at 2 different CPU. We call it multi-threading, because that application program could have several threads, so we call it multi-threading. Multiprocessing can have 2 applications running on 2 CPU. That is called multiprocessing. So multi-threading is actually you share the one memory, and with several multiprocessors, you have several threads going on to access one memory model. And multiprocessing means each of the process is independent. You don't need to depend on the memory of the other process to be finished. The last one is the conclusion for this overview. So basically, you have the basic instruction execution flow. I'm sorry. Click on the wrong button. And then you actually go optimize it by pipelining. Is actually in Japanese is called pipeline. And if you look at it, this pronounced as papunaika. Papunaika is a papunaika. And then it's a pipeline. Okay, and then actually architecture-wise, you don't see the difference. And then you have the super pipeline. Super pipeline is called super papunaika. So you actually have multiple execution stages, and actually break down each of the stage into 2. So you have a super pipeline design. So the flow is from basic to pipeline to super pipeline, and then from pipeline you go into super scalar, and in Japanese it's pronounced as super scala. The last one is the kanji is called ka, so super scala ka. And actually right here, you actually will have instruction execution, and then you execute 2 instructions at a time, something like that. So this one is a improvement from the pipeline. You have the super scalar, and then you have this called instruction translation. So microcode come in, so you have this instruction translation. Actually, it's a microcode. So from the pipeline, you have a microcode, or you from super scalar, you include a microcode translation. This in Japanese, this all kanji is called mele kan heikan. Okay, and then this mele heikan actually translation. The microcode go to the last one out of order execution. And then this one go to VLIW. So with the microcode, you can go to VLIW to have very long instruction word. And one instruction, you actually execute multiple tasks and then put into different processing unit as VLIW. And then this one is out of order. This is auto order. Auto order. So this one out of order translation, you actually can execute the instruction in different order, and then actually at the end you combine together and then write back. So these are the trend or the past how people develop a CPU of different flavor. And I would say right now we are in here with the superscalar and VLIW of some sort. We are in here for most of the modern day architecture. So the reason why I talk about this different architecture is that our compiler backend actually is to optimize it to serve in these different architectures. Now let's look at the assembly code. The assembly level, actually you don't see the difference between these different architecture. to it is a instruction set. And how fast can you execute the instruction set? It is the CPU designer's job. But from the assembly code writer, actually, you just need to write the code and make sure that the compiler will run faster. That's the interpreter, the assembler and machine code can run faster. That's all they need to know. So from C program, we have parser generate the intermediate code or the AST or the SSA, something like that, and then we perform optimization. And then we have a code generator generate to the target code, the machine code or assembly code, and then we get the object code. So assembly as target code for C, so that's one way you can compile your C code to object code, or you can use assembly code to assemble it to object code. And you can also have the function code to be translated to assembly code. And then you can actually combine all the code together to have to make one big program, and we call it separate compilation. So right here we have the process 4 from C double plus. We have the preprocessor, and we fed the data into compiler, and then compiler generate the .s code, and then you have the assembler to generate .o code, the object code, and the loader linker come in to help to combine the relocation of object code. Or you actually from the library, you combine them together to make one program and load it into your operation systems, manage the space for process edges, and run it. And we have this different assembly format. We have, and for the intermediate code, actually we have several formats. We can have the source code going to target code, and we may go through an intermediate code. So right here for Java, you have source code go to bytecode, and bytecode is the interpreter base, but we call it just-in-time compilation. So that's Java. And for C, we go through compiler and then executable code, you can run it. So these are different formats for intermediate code. And right here is instruction set architecture. We translate the high-level language to assembly language, from high-level language, and then to GIMPLE type instruction. And GIMPLE type extension go to this SSA type instruction, intermediate code, and then finally to assembly code, and then adhere to machine code. And machine code, each instruction have operand, and then memory access mode indicator, register operands, something like that's instruction set format, and you convert it from this assembly further to the machine code or object code. So that's the way we translate from high level to low level. And right here show you the source code. Object code is like this. And then you have loader to the hardware and you run it. And on the left-hand side, I believe this is a object code. The object code looks like this. This is the assembly-like description. But the memory location of the core of the instruction is like this. But this is relative. When they load your program, they can be loaded to different location relative to your starting point of your program. Assembly view. Assembly level view, as mentioned earlier in this course, compiler is simply a translator. It translates programs written in one language into programs written in another language. The other language can be almost anything. You can be source code, can be assembly, can be object code. Most of the time, it is the machine language for the available computer. So we, as a review, we will go over some of the materials most relevant to language implementation, so that we can better understand what is the compiler have to do to your program, what the certain things are faster and what are slower. So basically, the discussion for this assembly right here is to look at the assembly or instruction set architecture from the programming point of view. How can the compiler to do with this assembly code, and also how fast can they go, so that our target program will be running faster after the compilation, after our language design. And there are several different programming language and also many different machine language. So there are a lot of translation work to be done. Machine languages show considerably less diversity because they look similar. And traditionally, each machine language corresponds to a different computer architecture. But nowadays, the machine language can have different set for the same instruction set architecture. So it's more complicated than before. The implementation is how architecture is realized in hardware. And okay, in the last 30 years, the line between these are blurred. So yeah. Assembly level view, changes in hardware is one of the main driving force for the improvement of the machine. So changes in hardware have made new implementation techniques possible. So the architecture was also modified. You have RISC machine, and we also have these different CPU model, and also the level 1 cache and level 2 cache. In the discussion below, we will focus on modern RISC architecture with limited amount of coverage of their predecessors, the CISC architectures. And this is out of date. We will just pass it, because the workstation is actually it's only UFC PC now. It's nothing new. These are all materials. I probably need to delete all these. Now we are on lecture 3. And right here, I'm going to talk about the data path. This lecture is on data path in an architecture and the data type in a language. So data path is actually the data storage and data processing stages. In a machine, you have the control unit, you have the data path, and you also have the main memory. That's the organization of a main computer, main CPU. So right here, I show you the data path. Data path means you got the instruction from using the program counter to get an instruction to the instruction unit, and then you fetch the instruction, and then you actually load the data from register file to the instruction decode, and then you execute the program, the instruction, I'm sorry. It can be a loop operator or other operator sent to external core processor, or you actually have a floating point unit or something. Then you actually load, get the memory data ready, or register, wait for the data ready, and then you access the memory at this stage, and then execute it. And then eventually you actually have the result and write back. That's the basic pipeline. But in the bigger project, you actually can have multiple instruction running at the same time, and maybe out of order as well. So you would have the register renaming and retirement of register file, and reorder of the buffer, and your instruction decode queue will actually register a line alias table to realign it, and have the unified reservation station, and then actually provide to different low store unit, and also ALU, and also floating point units. And this is the modern days processor unit, but this is in one research project at Texas A&M. And data representation, the data type Un-SSA, you have the previous data type, character, integer, floating point, double, void, and derived data type, array, pointer, function, user-defined enumerator, structure, and union. And union, we see this in our calculator 3. That's a shared memory location for different data type. And actually, these are the C language. And what this related to our system is two things. One is the register and the instruction design. The other one is the memory access and the memory addressable. For example, like how to calculate the arrays index and also accessing the different elements in the array, or calculate the edges or the reference value for pointers and reference, and also how to call a function. These are related to the edges calculation for your processor, and also the primitive related to the data type and the number of byte reservation, big ending, little ending on your data, on your processor design. And the last one is this machine related, because you user defined. And right here are different data structure. And floating point unit also related to the floating point standard, IEEE 754, something like that. So right here, we look at the data representation in languages, and also trying to understand its relationship with the data path. And this is C#. C# has reference data type, and reference data type it has interface class data key. Data key, we talk about it, is like a little bit like lambda expression, an array. These three types, at least four types, usually are considered a reference type. You have the address calculation, you have the indirect addressing, those type of things related to processor, and primitive related to the size of the variable, and real type related to the floating point unit. And this is Java, similar to C and C#. And this is Python. Python, as I mentioned, is all object type. So basically, it is all reference type. It is on top of C, so actually, it's not a lot of things to talk about. You just treat it like objects. And then this is NumPy data type. It has different data type, but it actually will address to more like C direct data type instead of just operating what object type in Python. Okay, now let's, with the language aspect in mind, let's look at the memory hierarchy and data representation. Here's me for some water. Memory hierarchy. Why we have the memory hierarchy is because memory is too big to fit in one chip with processor. And actually, usually it's nowadays actually it's possible to build a single chip processor or single chip computer. It's totally compatible, possible, and it's totally realistic. And actually, it has been done for many projects. But to make the machine more powerful, usually you still want to have a bigger printed circuit board, or you also want to have multi-core, many processor, and have a larger memory hierarchy. So it's actually a decision about the system, how much thing you would like to have, and having a more complicated memory hierarchy will improve the system performance. So it may not be because of the real estate issue that the memory cannot fit into one chip. It may well be related to the performance nowadays. So right here, we look at this before, the memory hierarchy speed. And for the cache is used to improve the performance of the processor. There is a gap between your CPU cycle time and your memory cycle time. And CPU cycle time is in terms of half a nanosecond, or even actually it's like maybe only 1/3, like 3G, 3 gigahertz clock rate. That would be only 1/3 of a nanosecond. But memory cycle time nowadays, even is very fast, you still need to take maybe 50 or more nanosecond to complete a memory access. So it's probably 1 to 100 ratio or even more. It is not realistic to actually let the CPU wait for your memory to respond. So there is a study for how to improve the performance of your CPU, and at the RISC project at Berkeley and the follow in RISC processor, they study the memory hierarchy of having a cache between the CPU and your memory to fill in the gap. The observation is your CPU actually working on only about 10% of your code on about 90% of the time. So that means that if you can get the 10% of the code or even less onto your processor or nearby your processor, actually that will be actually improving the performance of your machine. Even though you may have the penalty for the other 10% of the time that you may have a cache miss, you don't have the data ready for you. In that case, actually you still just the penalty, just the regular memory access. So it is not really that huge. So then there is the study of the memory location and memory size for the cache. So there is a study for individual cache size and the miss ratio. Miss ratio is no good. If you have miss ratio, that means you actually need to access your memory. In that case, you will pay the penalty for memory access. Now, then the question is, how much cache is enough for your problem? So the study show somewhere around 1K to 10K, 1K to 10K to 100K. These will start to saturate, and then after that, the improvement is no longer that obvious. As long as it drops below 10%, it will become more acceptable, as I mentioned. And if you look at the level 1 cache and level 2 cache, if we have a 8 kilobyte level 1 cache and 8 kilobyte and 16 kilobyte, you will see that the 16 kilobyte level 1 cache with level 2 cache of maybe level 2 cache of actually, if your level 1 cache is 16 kilobyte, your level 2 cache actually almost not mattering at all. It will guarantee to have a hit ratio, that is 1 month miss ratio of over 90%. So these are acceptable in all cases for no matter how large is your level 2 cache. So that means 16 kilobytes level 1 cache is good enough to get more than 90% of the hit ratio, or 10% of lower than 10% of the miss ratio. That's what I say. You know, your program operate on maybe only 10% of your code for 90% of the time. That's the main rationale behind cache. And you have the level 1 cache. The relationship of level 1 cache and the level 2 cache will be also similar. So you try to build up 1 level, 2 level, or 3 level of the cache. The real time that you actually need to access a main memory is actually very low, maybe even lower than 1%. That you need to actually within a class, a instruction cycle need to access the memory. So that's the purpose of having cache. Some of these levels are visible to programmers, some of them are not. For our purpose here, the level that matter are register and main memory. So caches actually have no programming meaning, or nor actually in instruction level you won't see it. Excuse me for some water. At instruction level, actually you won't see it. Registers are special locations that can hold data that can be accessed very quickly, because register is on-chip memory unit, and actually in the data path it's even faster than the cache, level 1 cache. So typical RISC machine has a few set of registers that are used to hold integer and floating point operands. And make the better use of the register can improve your performance of the CPU as well. Memory hierarchy. It also has several special purpose registers, including the program counter. The program counter is used to hold the address of the next instruction to be executed, usually incremented during the fetch execute cycle. And there's a process status register that has all kind of flag. You have a floating point unit flag, overflow flag, those kind of flag are in the program status register. Whole variety of bits of little interest in this course actually is we talk about more about the optimization of compiler, and these are the real hardware implementation, so not as interesting. Data representation. Memory usually is bi-addressable, meaning each 8-bit piece has a unique address. Data longer than 8 bits occupy multiple bytes. Typically, an integer occupies 16, 32, or recently 64 bits. A floating point number occupies 32, 64, or recently 128 bits. Here are the computer numbers. You have integer and the float. For an integer, you have hexadecimal integers, digits. You have 0 to 10, 10 is 8, and then B, C, D, E, F, F is 15. And then you have 4 two's complement number. And actually, two's complement number, you study from 0 to 2 to the order 3 minus 1, that's 7. And the negative number you study from -1 to -2 to the power 3. So this is the 4-bit two's complement number. I'll explain the two's complement idea later. And then you have a floating point number. Floating point number, usually you have a sign, you have the exponent, you have a fraction part, or sometimes it's called mantissa, depending on the language. And then this is IEEE 754's floating point standard. The idea is you normalize the floating point number will be 1.f. So actually, the leading one is not shown in the memory storage, and then it will be 1.f times 2 to the power e minus b. B is a bias. So actually, Actually, this, if it is 1024, you will be power 1. 1023, it actually will be the number exponent will be 0. So that would be 1 point something number. Data representation. It is important to note that unlike data in high-level programming language, memory is untyped. Because memory actually is just binary data or hexadecimal data. So there is no format. It just being accessed by different instruction. That's it. Operand are typed in the sense that different operations are typed. So actually you have the floating point unit operation and also have the integer operation depending on how you interpret it. Typical data format including instruction, integer, and floating point. Data representation, other concept we will not detail but covered. We will not detail but covered in other courses. Here we have big endian and little endian. We will show this later actually. We have integer arithmetic, two's complement arithmetic, floating point arithmetic, IEEE standard. Now we shown this already. First, let's look at the big endian and the little endian. Little endian is more often used by Intel processor. Little endian means the lower address store lower bytes. So you have D7C4, so lower weighted bits store in lower address byte. That's little endian. You're ending at the little number. And on the other hand, big endian, you have the higher bytes store lower weighted byte. So this is just a convention of how to store your data. But when you load data from memory to your register, you need to know which one means higher bit and which one means lower bit. And also when you do the programming, that actually you read in some byte buffer. For example, for Java, you had a big integer, big decimal. You need to be careful about which byte is interpreted as of higher weight instead of lower weight. And here is one example. Let's look at this bit endian case. In bit endian case, this higher byte for this is memory integer from locations 432. Higher byte means lower value, so you actually have a number of 000000037. That's your number. It will be interpreted as this. For little endian number, actually this should be stored as 37000000. For higher byte, you store 00. So and down to the lower byte that you store 37. Now let's look at processor arithmetic. First, let's look at the conversion of binary to decimal and decimal to binary. To convert from binary to decimal, you actually has the binary number right here, lower weight here, higher weight here, and then you put on a weight, and then use the weight times your number in binary data, and sum them up, you will get the decimal value. But you must assign the right weight on each bit. To take conversion from decimal to binary, each time you divide it by 2, and the remainder will be the digit that you have, and this will end up to this. This is the conversion from back and forth. And to convert from decimal to binary, you have a number, and then you divide it by 2, the remainder put in here. And then you have 78, you divide it by 2, you put the remainder over here. And by doing that until you have 1, and then you read from here, it will be, this one is the last one, it will be 100111100. That's the number 156. So another look at this, you have 202 divided by 2, put the remainder 0 over here. 101 divided by 2, you put the remainder over here. Keep doing that until you have something that you don't need to continue to divide. And read from the bottom, you will get 11001010. That's the number 202. Here is the idea for the two's complement. The two's complement, the negative number for two's complement represent as such. Your minus x is represented by your largest number, that is 1111. That's the 4-bit largest number, minus x plus 1. When you minus x, that is called 1's complement, plus 1, that's called 2's complement. And by doing this, actually you end up with x plus minus x. If minus x defined as this, you will end up with x plus 2 to the power x, a minus x. That will give you 2 to the power a. Then because of the memory storage is only 8 bit, then this is actually will cause a overflow. And that overflow can be ignored to get a 0 for the value. And that's the result for x plus minus x. So a number 0, 1, 0, 0, you find the 1's complement first. It will become 1, 0, 1, 1. 1's complement is by the largest number 1111. Use that number 1111 to minus your current value. And actually, you just flip each of the bit. Your 0100 will become 1011. That would be your 1's complement. And then you add 1 to this number, and then you get this 2's complement. And theoretically, this 2 to the power 8 will be overflow. So forget about it. The sum will actually, this number will become 1111, 1111. That is the negative 2 to the power, 2 to the power. This is actually this actually is the positive, large is the positive number in this 8-bit format. So now let's look at how to find the 2's complement. You have number 79. You actually flip the value from 1 to 0, 0 to 1. You get this. And then you add 1 in, and you got this minus 79 in 2's complement format. And here is the set of Java special number rule. And actually, this is actually following the IEEE 754. And we covered this already. We will just skip here. And for binary addition, you have the rule for the data 0 plus 0 equals 0. And then you have 1 plus 1, you carry 1. And something like that. I will omit this one actually. And minus 1, you need to have A, and then make B to be converted to the 2's complement. And actually, you sum them up, you get the subtraction. And this is the ASCII code. When you have a string of character that will be stored in this format. And ISA-related programming language and compiler design. Instruction choice. These are the issues that you need to take care of for compiler design. You have the instruction set, finding the proper processing unit, memory address mode to reduce the memory access latency, big endian, little endian, data storage format, and integer and floating point arithmetic, and loop unrolling, superscalar, VLIW, pipelining, super pipelining, code reordering, optimization. And these are the things that we would discuss for ISA for compilers. Instruction set architecture. The set of instructions executed by a modern processor may include the following. One is the data movement. You load data from memory to register, or you store from register to memory, or you push or pop. Actually, that is actually operating the data from your memory, doing operation on your memory, push and pop to change the content of your stacks. And also you have move memory, swap, register, those are memory operations. And you have arithmetic and logical operation for negation, extend, that's sign extension, add, subtraction, multiplication, division, and or shift. And these are two types. One is memory, one is the arithmetic, ALU operation. Another one is the control transfer, jump, call, trap, and jump into the operation system, that's the interrupt, and return from call, and or trap or conditional branch. These three types. One is control flow, one is logic, one is memory. And three instruction type: computation, that's ALU type, data movement, and control flow. So that's here we have three bus for the CPU and the memory. So basically you have computation that happen on the processor itself. Data movement is talking about using your data bus to reach the memory and using address bus to fetch your memory. And then control flow actually is jumping from one program to the other that also need to access the memory and also need to access the memory and doing sometimes you need to switch the content of your procedure or process. Instruction set architecture in address mode. The address mode actually related to how you find your data or how you find your program call. And usually for array or some composite data type, you need to use the relative indirect addressing or relative addressing. So you would have different address mode. One is the data in instruction, that actually in the instruction you have the instant data, and you have data in register. You have the address of data in instruction. That's the direct addressing. And then you have address of data in register, that's indirect addressing. And then you have address of data computed from two or more value contained in instruction and or register, a more complicated address mode. And on-RISC machine, ALU instruction use only the first two of these address mode, load and store. So in RISC machine, actually you have more of the register mode, data in register, or using address of data in instruction. On RISC machine, all address mode are generally available to all instructions. RISC machine typically have the richer set of address mode, including some that perform multiple interaction and or arithmetic computation on values in memory in order to calculate effective addresses. So RISC machine have more complicated address mode, and that would take longer time because you get some data from memory as address, and then use that address to access another memory that take longer time. So right here is one table for the address mode. The first one is register mode. You directly access some register number N. Second one is called index mode. You use the address of the register N as a base, and then plus certain offset value to access some memory address that usually used for array. It's called index mode. And then the third one is symbolic mode. You actually use your program counter plus some address. That this usually is used for relative to program counter, that usually is for function call. And then this one is called absolute mode. You use @ sign with address in your assembly code. The word following the instruction contain the absolute address. And then the next one, indirect register mode. You use the register as the pointer to the operand. So that is used as the indirect register mode. And then the next one is indirect auto increment. And then you use the register as a pointer to the operand, and then you increment that to, that's used for pointer or object data fields. And then intermediate mode, you have number N, the word following the instruction contain the intermediate constant N, and that actually is for constant or literal. So this one is the fastest. And now this is another table for the address mode. We have register mode, PC relative mode, base plus offset base relative mode, in immediate mode, and interim mode. So these modes are similar to the previous table, but here show you the format of what it is. And let's look at the intermediate mode. So for example, this actually right here is the register access. So you use the base register and then with offset. And this is used for jumping to a certain address. For this call the, actually, let's go back to the previous page. This is actually this index mode. And it's shown right here with the base register and the address offset. So this table shows you how different address mode is represented in the instruction. And this instruction set is of 16-bit. I believe this is a very simple microprocessors table. And then here are the functional group. For the instruction, you have move instruction, MOV, you have math instructions, and multiply, division, add, and subtract, logical operation, and or, and this is inclusive, or negation, and then rotate shift instruction. This is shift right, and they have A and R. Actually, I don't remember what is A stand for, sorry. But you can look at table here, maybe you can, because each instruction set have different names, so you have to look at the instruction set. And then bit operation, bit set, bit clear, and bit tested or set or something. And this one should be bit toggle, so from 1 to 0, 0 to 1. Compare, skip, and branch, these are the branch one. This B should be branching, and C should stand for compare something. This is equal, compare. So this usually have to look at the instruction set description or menu to understand what that it means. And then flow control instruction, branching or call some functional routine. And then stack operation, push and pop, those kind of things. Control instruction, this NOP is usually used, it's called no up. No up is very useful, especially when your instruction is waiting for something that you need to, that the CPU to be idle. You need this no up. And reset the CPU, you have a reset. Sometimes it's used and power save more, and this is actually used when you have loading some new program or something. You may need this. DSP operation, you have the multiply, add, accumulate, those kind of operation. So your instruction might divide it into such a group, so many groups. And each one will implement certain function in your language. Let's look at these conditions and branch. All instruction sets provide branching mechanism to update the program counters under program control. Branch allow compiler to implement conditional statement, subroutine, and loops. Conditional branches may be controlled in several ways. Here is an example. You have A assigned by B plus C, and then if A grade equals 0, then you go to the then part of your if statement. So right here, first we move the content of the register EAX to C. I'm sorry, you move the content a long word from C to the register, from this way to here. So you load the memory C to register X, and then you add the content from B label to this register. And then, so this register now is stored with the B and C, and then you move this content to the memory address A, so that's a store operation. And after that, you check this register. I'm sorry, you check this register. You check this A. If it's not equal to 0, it jump to here. Otherwise, you go into this branch body. So this is actually in the opposite logic to this statement. So the first 3 instructions all set the conditional call. These 3 will set a conditional call that usually stored in the PSR, the process or program status register. And then this jump statement will be looking at that program status register to check the test condition, and then you will perform jump if it is if it is not equal to 0, you will jump. Otherwise, you will go into the if then block call for body. Conditions and branch. For cases in which the outcome of branch depends on a value that has just been computed or moved, most machines provide compare and test instruction. Again, in the 86 architecture, here we have if A less than or equal to B, then body. So we move A to the register, and then compare B with A. So if B is greater than, B greater than, when we compare, jump is greater than. So actually, if A is less than, so we compare this register with the compare. So if A is greater than, then we actually jump to here. And otherwise, it means that A is less than or equal to B, we go into the body. So this side we have if A greater than, then we'll go to body. So right here, we actually compare the register content as A and then compared to 0. Okay, if less than or equal will go to here. Otherwise, it will be greater than, so you will go into the body. Okay. ISA will make a difference in performance. Of course, you have different instruction set. That means that basically you will decide how many cycles you will need with different instruction set, and that number of clock cycles will determine your performance if the clock rate is the same. So then whichever instruction set provide you the higher flexibility to program to provide the machine code for your language, that will give you a better support. So on x86, the code fragment of this maxima function might naively be translated to here, but if you do some optimization with a conditional move instruction, it can become something like this. So one conditional move operation is a conditional move operation can actually reduce to 5 instructions instead of 1, 2, 3, 4, 5, 6, 7 instructions, and you get a better performance of actually about 40%, 5 versus 7. A few instruction set, including 32-bit ARM or IA64 Italian processor, allow almost any instruction to be marked as conditional. This more general mechanism is known as prediction. So actually, with prediction, you don't need to write. You will save a lot of time on this jump operation because you predict, and if that doesn't work, then you can just squash the whatever result you have done by prediction, and the jump function, the time can be greatly saved. Instruction set number 1 and number 2, lecture 7. Right here, we again look at this chart to remind you what is the progress of different processor style. So architectural implementation, as technology advances, there are occasionally times when other threshold is crossed that suddenly make it possible to design machine in very different way. One example of such paradigm shift occurred in the mid-1980s with the development of RISC architecture. I believe that the shift is because the single chip processor unit is possible. At that time, you can put more function into a single chip, and because everything is on chip, you can basically optimize for the database and the latches to allow pipelining, and also you can have more uniform clock rate and do not depend on the memory access so much. And besides that, you can put on-chip cache that actually make the RISC machine to be able to perform better with uniform instruction clock cycle. So that's why when technology advances, you may put more transistor onto the chip, and by doing that, you can improve on the architecture as well. So architectural implementation during the 1950s and the early 1960s, the instruction set of a computer was typically by soldering together a large number of discrete components that perform the required operation. So to be a faster computer, one generally design extra more powerful instructions. So trying to use more complicated instruction to make it faster. And this has unfortunate effect of requiring assembly language programmer to learn a new language. So every time they change different assembly language. And then IBM hit upon an implementation technique called microprogramming. So with that, you pre-store some instructions, sets a basic operation into micro codes and allow microprogramming. So there is some sort of memory nearby the CPU can be used. So basic idea of microprogramming, build a micro engine in hardware that execute an interpreter. So your program instruction is interpreted in firmware. So then the interpreter implement in IBM 360 instruction set. More expensive machine had fancier micro engine. So at that time, microcode is off chip, but provides some sort of speed up already for the implementation of CPU. And at that time, CPU is not one chip yet. Microprogramming makes it easier to extend the instruction set. People ran studies to identify instructions that often occur in sequence, then provide new instructions that perform at the function of the sequence by clever programming in firmware. So this is all old stuff. And then the microprocessor revolution in late 1970s occurs when it became possible to fit micro engine onto single chip. So this actually marked the main difference. The late 1970s, the produce of the introduction of microprocessor, and that is the time that personal computers were born. So by mid 1980s, Microsoft is founded around the year 1980s, and at that time, that's the born that marked the the personal computer era. And then by the mid 1980s, VLSI technology reached the point where it was possible to eliminate micro engine and still implement processor on a single chip. And then that's the time that RISC machines start to replace the CISC machine. And architecture implementation with hardware-only processor on one chip, it then became possible to apply certain performance-enhancing tricks to the implement. But not only the instruction set was very simple and predictable, this was the RISC revolution. And after the RISC revolution, we never go back. Its philosophy was to keep up nice, fancy features in order to make common operations faster. So two things drive this. One is one-chip processor. The other one is on-chip cache. And by having this, we improve on the clock cycle for uniform clock cycle, and that allow pipelining. With these different architectural advances, we make this RISC possible. And with RISC, we have higher performance processor and more uniform instruction set, and then drive the following actually that RISC drive all different optimization and RISC following that possible. And then RISC machine. RISC machine, a common misconception is that small instruction set are the distinguishing character of the RISC machine. No, small instruction set just means, I should say, the main distinguishing characteristic is not small instruction set, but uniform instruction set that make the RISC machine better than CISC machine. Better characterization, RISC machine are machines in which at least one new instruction can be started every clock cycle. So uniform pipelining that make the RISC machine possible. All possible mechanisms have been exploit to minimize the duration of a clock cycle and to maximize the number of functional units that operate in parallel during a clock cycle. So you try to make the instruction uniform, and then you try to make the instructions, try to explore the instruction level parallelism. These two are the way to improve the performance of the machine code. Reduced cycle time comes from making all instructions simple and regular. That's a uniform instruction. Simple instructions never have to run slowly because of extra logic necessary to implement the complicated instruction. So try to make it simple. Try to make the 90% of the code more efficient. You can keep up the 10% convenience, but focus on the 90%, and also keep up the complicated memory access mode, not only used for 10%, but maximize the caching for the 90% of the program. That's the spirit of the RISC. Focus on the 90% that is most commonly used. So maximum parallelism comes from giving the instruction a very regular and predictable format. The interaction between instructions are clear, and the processor can begin working on the next instruction before the previous one have finished. So that makes PUB19 possible. Now let's look at the PUB19. PUB19 is the first thing that we look at. PUB19 is the first stage that improve on the processors. So PUB19, you actually cut the instruction into 5 stages. So you actually can share the data pairs and have a degree of 5 improvement. That's maximum actually. Sometimes there is certain memory access take a longer time. The instruction need to wait, and then we allow the out of order execution, but still you are not able to get a parallelism of degree 5 by using PUB19. A degree of 2, 3 will be good enough. So PUB19 is probably the most important performance enhancing trick that happened on the RISC machine in late 1980s and early 90s. Compiling for modern processor, the processor have to be careful not to execute an instruction that depends on the previous instruction, so that's data dependency. The compiler can improve the performance of the processor by generating code in which the number of dependency that would store the PUB9 is minimized. So that this part is how we do the code optimization. Either you are doing it in actually this data dependency can be avoided even in the bytecode level, the intermediate code level. Try to minimize the dependency. So that's why you have a single static single assignment as SSA optimization, and you put in those 5 functions to improve that. There are 20 different optimization steps in GCC. That's what we talk about. And basically, not only that, you still need to look at your instruction set for the machine-dependent part as well. And that is why we're talking about a modern processor improvement. And in fact, in our very early discussion in this chapter, we actually had the instruction set, and then we developed the compiler. At this time, the optimization of the compiler and the instruction set can be done together. Actually. It's co-design status. So to optimize the compiler, we need to take care of the dependency. flow dependency, control dependency. Flow dependency also called control dependency. The other one is anti-dependency, and another one is output dependency. So 3 different dependencies. And I believe this flow dependency is more serious one. And you also need to take care of the branch, and branch can cause delay. Let's look at them. So flow dependency, anti-dependency, output dependency, and branch. Let's look at it. First one is flow dependency. Flow dependency happens when your outcome will be the input for the next instruction. So this actually will lock up a lot. Let's look at the instruction. Let's look at the instruction. Okay, let me move up to this one. So right here, if you have data ready here, okay, data ready here, but your next instruction need the data here, and you are not able to supply it. So you have to delay this instruction until here, so you can pass the data down. So you will create 2 cycles by that control dependency. That will cause you 2 cycles. And this one is called anti-dependency. The input of this need to be released before the output can write in. So let's look at this. Let's look at this. The input is right here. You need to do execution, and then the other one is write back. So if this actually need to get it from memory, it takes longer time, and this one try to write back, sometimes it cannot be performed, especially if the data fetch of this instruction is from register. It might finish and want to write back, but this one still access the memory, then that will create that anti-dependency. This can be removed with out of order execution that we talk about, the out of order execution. The out of order execution, let's move up. The out of order execution, when you try to actually write back earlier than the previous one, this is called the actually the anti-dependency can be avoided by out of order execution, but the control dependency is not okay for out of order execution. So this one can be solved by hardware, by the design of the instruction set and the pipeline and data path. But this one had to be handled by compiler. That's the part we look at it. So that's the data dependency. Another one. Okay, one thing I need to talk about for the previous channel. I don't want to skip it. Right here, when you have something that you cannot do, you wait for something. This is called data dependency. Then we create something called bubble. For bubble, then right here you have no instruction can be scheduled on here. Then that's the time we put some no up. If that really happened and nothing can be done, then that's where we put this control instruction no up into the processor. No operation will be inserted over there to make sure that the bubble is handled. So still some execution, but no up. Control dependency graph. So actually, this graph for the source code is like this, and then the control dependency will be analyzed by using this graph to analyze whether there is a control dependency of certain operand or certain register, because you have input 1, I1, and then this is instruction 0, is instruction 1, instruction 2, something like that. So there is some branch condition, and also analyze the dependency of the data. So this actually on this side, as you can see right here, you also use some sort of the control flow graph to help you to optimize the control dependency and also help you to do branch prediction. So you will see there is a branch prediction that can be looked at from this control dependency graph. And this can be done when you do the at the intermediate code optimization. So compiler for the modern processor try to minimize the processor stall. Processor stall means the pipeline stop, and we use the no up if there is some stall. And other than that, load and branch take longer than ordinary instruction. Load have to go to memory. That's slow. Branch will disrupt the pipeline, and this need to be avoided all by the compiler. Processor have interlock hardware. Early risk often provide delay slot for the second or insertion of no ops. The instructions in branch delay slot get executed whether the branch take occur or not. This is squashable instructions. Compiling for modern processor, we can insert the instruction in the low delay slot, can use the loaded value. As pipeline have grown deeper, people have generally realized that delay slots are more trouble than they was. So that actually delay slot is not a good thing right now. Most current processor implementation interlock all load, and so you don't have to worry about the correctness of the issues of low delay. Sometimes machines still have branch delay slot, so they can run code written in the late 80s. Okay, later implementation provide nullified alternative. Nullify means squash. You can just predict, and if it fails, it just it's a little bit like the backtrack in the recursive descent algorithm, except that this time you actually try the true part and false part and just squash the one that doesn't happen and return the processor back to the right status. Let's check how many pages we still have. We are at 97. We still have about 20 pages. Let's move on. Okay, the next one is compiling to a modern machine, risk versus system. Okay, right here, I would say this topic is a little bit old. Let's look at the processor chart right here. Because of the instruction translation, we decode it in on-chip microcode, and we have renaming for register. We have the reservation station. We have the out-of-order execution. So recently, the so-called CISC and RISC are no longer that important. We take in a lot of the advances in RISC machine, and we somehow made the instruction set more complicated than before. But all of these are okay with pipelining, superscalar, the instruction translation, and out-of-order execution. These are all commonly used, and more hardware support. So this CISC and RISC comparison that's been described in the textbook is no longer that important. So unfortunately, this is okay. Most recently, CISC machine, RISC machine, are also called a superscalar implementation. These are already old already. If it is a signal, if it is a CISC machine, the number of instructions per second depends on crucially the mix of the instruction by compiler. And actually, yeah, this is true. The CISC machine, you have to optimize so that your number of instructions per second will be improved. But this is the Pentium 3 time. This is not important. It's old. As technology improves, complexity begins to creep back to RISC design. Right now, we see RISC machine with on-chip vector unit. We start to have a floating point unit. We have a superscalar. We have the low store unit, and we have larger cache. That's the common chain. And vector processing means like if we have the scalar operation, we try to do an array summation of AI plus BI, then we have to do one statement after a statement. But this actually can be done if we do this. We have a vector A1 to AN plus B1 to BN, and then the sum is C1 to Cn. So we can use a whole array A, B, and then maybe sum together, or they multiply together, and then feed back to some unit. Of course, the N might not be perfect. Say we have N equals 70, but we only have 10 vector processing unit. Then you can just do a certain section of the vector at a time, and then maybe you cut it into 7 parts to fit into the vector unit. So that's also part of the task for compiler. We also see CISC machine with RISC-like subset. So this actually CISC also moving into RISC way. So right now, actually, CISC or RISC is not that important anymore. In the future, we might see large amount of memory, multiple processor, network interface. This all happened already. And additional function DSP, this all happened already. And as I mentioned in the beginning of today's lecture, we have the TPU that's even more powerful than DSP or GPU. That's machine learning, deep learning engine is coming up soon by Google. Compiling for modern processor, in addition, the 8086 instruction set will be with us for a long time, still there. And after a failed attempt to introduce its own RISC architecture, Intel worked with HP and the RISC like IA64, but it's about 10, 20 years ago. It's old already. We skip those old stuff. In a sense, code for RISC machine resemble microcode. Yeah, the early day we have microcode off chip, but now it's on chip, and that actually is not in firmware anymore. It's in a microcode translator, and that actually in that microcode is in database. Let me try to find something that we talked about before. Let's go back to our chapter 1. Our chapter 1. Not here. Session 1, our chapter 1. Let me see. Chapter 1 right here. Let's bring up the chapter 1. The microcode, actually, we have one example. This is the microcode. Nowadays, microcode, it actually fetch the instruction, you decode and get a microcode, and then it got executed. So the microcode is no longer off chip, but it actually have the microcode roam on your chip, and actually is part of the data path. That's the modern day microcode, and you have the instruction to microcode translation. So this is actually one interpretation. You get one instruction, you actually interpret it into a program of microcode, and that fetch the microcode memory that's on chip in the data path. And that is what one of the recent advancement. We go to the 105. One of the modern improvement that we have, the new microcode on chip. And it also bundled with the register renaming, so that actually you don't need to depend on certain register name. You can use different register to help the microcode to process much faster. And this chip, this is old, the Pentium and 486, that's old. Compiling to modern processing unit. Multiple functional unit. For superscalar machine can issue more than one instruction per cycle. So as long as they are compatible, and let's look at it. Let's look at the architecture. Say you might have multiple load store unit, you may have multiple floating point unit, and then you have branch unit and integer unit. So those can be run in parallel. So you can utilize the superscalar architecture. So you can utilize superscalar or VLIW architecture and run multiple instructions at a time. So that actually explore the instruction level parallelism much more. And compiling for modern processor, because memory is so much slower than registers, keeping the right thing in register is extremely important, especially the good combination of register and caching. This machine often have at least two classes of registers, so that they don't have to support all operations on all registers, which the compiler have to keep track of. So the idea of register window actually save memory access time. So we have the code frame for each procedure, or and if we need to swap your get the data from your memory stack, then it takes a long time. And if those code stack is in your CPU, in your register, then your speed will be much more improved. So if your stack is stacked like this, your local variable, your temporary data, your register parameter, if they are organized like this and then organized like this, it will be much faster. But because register is not like stacked in the memory, they have very large area. So it is very easy for you to hit the boundary. So we start to have the circular register file. Even physically, they may not be stored this way, but you will wrap over and then process this like a circular way. So you have process one, you call another, now process two will become on top, and then process three, something like that. Keep rotating until they hit together. Then you maybe need to do some process to memory, register to memory operation for load store for the whole frame. And this can be done while your CPU doing heavily on the register. You can use the load store unit to optimize the performance for the register windows. So compilation of a modern processor actually to overlapping the register window. Good register allocation scheme sometimes will conflict with instruction scheduling. So there is a certain study need to be done to optimize the register and the instruction scheduling. And instruction scheduling and memory register allocation often conflict. So that is between your intermediate code or the and the memory register allocation. So the optimization for this actually, when we talk about, let me see, our talk about the overview. This one. Remember that we talk about the compiler backend. In the compiler backend, we have the register allocation, instruction schedule. These two are actually conflicting at the backend. So there should be something that you need to actually optimize, especially for the pit hole as well. So this part needs to be optimized, and that's how the architecture for your CPU, for your processor, is very important, and that it's hard to say right now which one will be more important, because that depends on CPU and your program, and that have to be decided by the compiler. That's why more than 20 steps of optimization is needed in the compiler. It's very complicated actually. To make all instructions of the same length, actually you try to make sure the clock cycle is uniform, operation is uniform. That's why the on-data-based microcode become popular. Summary: some major RISC architecture are these. These are RISC architecture, and some current development for Intel and AMD, they're still using the 64-bit addressing, but they still considered to be CISC. They have complicated address mode. But somehow these two right now are hard to say which is RISC, which one is CISC, and because of the architecture improvement. Compiling to modern processor, number 4, multi-threading and multi-core. Advances in processor technology, it gives you faster clock, a higher level of instruction level in parallelism, speculation. To keep the pipeline full, modern processors guesses which way control will go at every branch, and speculatively execute the instruction along the predicted control path. And actually, this improves performance and larger caches. And in technology, for the architecture, we have pipelining, super pipelining, superscalar vector processing, VLIW, instruction translation to microcode, reordering of the microcodes, and renaming of register. These are all used for the architecture. And x86 architecture, right here we have a processor implementing the IA32. That's the example we are going to look at. It has a protected mode, real mode, and system mode. And these are 3 different modes for the architecture. Protected mode is the normal operation. Real mode is a highly restricted operating mode in which only the first megabyte of the physical memory is directly accessible. And these two are not discussed here. System managed mode, that's these are for special purposes. Usually it's run in protected mode. A processor implementing Intel 64-bit architecture has about 3 modes plus a IA32 mode. So it has its own 3 mode and the one IA64 mode. So actually, processor not only had the instruction set, but also had different operation mode, so that it can mimic the IA32 or the system mode to do something more than just normal 64-bit mode. So here is a x86 architecture's register set. And basically, they are 8 32-bit process control register that's dedicated for process control use. I think it's like CR something, it's not shown here. And there is 4 16-bit table register, GD something. So these are not shown here. And then they have the debug register, DR something. And then they have the file test register and memory range register and specific register, machine check register. And these are the registers for general purpose. And then this is the instruction set for i86. Right here you have system, MMX, SSE, virtual machine, 64-bit mode, special instruction. The integer instruction probably the most important, and the 14-point unit. And then these are the low store unit, I think. SSE, SAE2, SAT3, SAE4. So these are actually for each functional unit. And then this is i86 architecture. This is a McKinney project, but this is already old. It is still very informative for you to learn new architecture, but this is quite old already. And it has the instruction fetch, instruction cache, and then instruction queue, and then register renaming system. And you can put in several instruction, memory access, branching prediction, and floating point instruction, and then do renaming things, and then map to different processing unit to run at the same time. And this is a conceptual diagram for this. And x86, we have the address memory. Here is how you actually calculate the address. And I don't go into detail for this. Just show you the x86 architecture. Just show you the x86 architecture. And it is using the little endian scheme. You can look at here by yourself. And this is the flag register or the process status register for different flags. So they are overflow flag, overflow 11, overflow flag, something like that. And the compiler need to check this for those flags and proper instructions. And here are the exceptions handling interrupts. Okay, we briefly go through the x86 architecture, and I believe on our website we have more information, and this will take a lot of time, but I briefly use the x86 architecture as our conclusion for this chapter. And in fact, we also have ARM architecture in the textbook, but I don't want to go through that. And just thank you for watching this video and finish this chapter. And this one actually just cover the architecture for the real compiler issue that will be in the chapter 15. And right here we have covered some part for the backend for the compiler, but chapter 15, I'm sorry that in our schedule we don't have time to work on that. And after this, we'll go into the unit 2 for the language features, including the control and the data and object-oriented programming. And then we follow by chapter 13 on the concurrent programming. That's the second half of this course. Thank you. Bye-bye.